Let's look at this last problem of this AMC10 test. How many ways are there to place 3 indistinguishable red chips, 3 indistinguishable blue chips, and 3 indistinguishable green chips in the squares of a 3x3 grid so that no 2 chips of the same color are directly adjacent to each other, either vertically or horizontally? Obviously, this is a counting problem, and the description of this problem is not very hard. So I guess many of you may be able to jump on it and play with it for a little bit, right? But after a couple of minutes trial, some of you may have found that it's sort of non-trivial to keep your analysis organized. Then some of you may wonder, what is the right approach to analyze this problem? And my answer to that is, the right approach for this problem is always to pick your favorite or a very special square so that you can place a chip in and start analyzing its neighboring squares. And gradually, you want to pan out your analysis to the full square. That is the only correct way to handle this problem. And of course, with your solution, or maybe your partial solution, you can compare that to other people's solution, and then try to determine why others' choice is different from yours. What made you to make that choice? This is the only correct way to learn from this problem. And in this video, I'm going to introduce 2 ways to solve this problem. And in both ways, we'll apply 2 important principles. One is to consider the extreme or special scenario. And the second principle is to use casework to help out our analysis. The first principle will help us to get started in the right direction. And the second principle will help us to sail through our analysis in a more organized way. And as I pointed out in many of my other videos, that the casework principle is always a good approach for problems like this. Alright, let's get started. So let's call the first method M1. And then we'll draw a grid of squares first so that we have a more direct view of what's going on. In this grid of squares, we have 9 cells. The question is, where should we get started? And as we mentioned that we want to pick a very special place. And this square is so special that it has some different properties than other squares. Alright, before we actually do that, let's read the original problem again. In the original problem, there is only one crucial condition that you have to satisfy. That is, no 2 chips of the same color are directly adjacent to each other. Therefore, we know that no matter which square we pick, the next step has to be its neighboring squares. Therefore, we want to consider our extreme case in this direction. We want to pick a square with the fewest neighboring cells. And out of these 9 squares, which of them are of this property? And it's not hard to get our candidates, right? We know that only the 4 corner squares satisfy our requirement. And by symmetry, we can certainly start from any of them. So let's say we start from the bottom left. This is our starting point. Then the immediate question is, how do we place a chip in it? And since we have 3 colors of chips, and of each color the 3 chips are indistinguishable, therefore we only have 3 ways to place a chip in it. That will be either a red chip, a blue chip, or a green chip. So we have 3 ways for the first step. And by symmetry, let's say we placed a red chip in this square. Then in the next step, we want to consider its neighbors. For both of its neighbors, we can't place a red chip in. Then what's our choice? We certainly have different ways to fill in these 2 squares. And now it's a good place that we do a casework. How do we split this problem here? A natural criteria that we choose here is these two squares are of the same color. So basically, we put two chips of the same color in them. Then that is same color. So this is our notation for the first case. And then in the second case, we'll place chips of different colors in them. So that will be different colors. Good. So let's consider these two cases one by one. In the first case, if these two squares are of the same color, and we only have two colors left, therefore, we have two ways to fill in these two squares. So they can be either both blue or both green, right? And by symmetry again, let's say we put two blues in them. So two blues. And now we want to consider the rest of the 6 squares. Remember, we still have 3 green chips untouched. Therefore, at this step, it's best that we consider these 3 green chips, since we only have 6 squares left. Then we know that there shouldn't be too many ways to place these 3 green chips, right? And a natural choice will be to place the 3 green chips diagonally in this way. And of course, you know that there might be other ways, but this is a good criteria that we split the first case into some smaller subcases. So let's denote the first subcase as diagonally. Diagonally. And that is for the third color, right? We want to keep the third color diagonally in this way. And then certainly the second subcase will be we place them elsewhere, which means at least one of them are not in these 3 diagonal squares. They got to be in here, one of these 3 squares. So let's call that non-diagonally. Non-diagonally. All right, so let's consider these 2 subcases one by one. When we place these 3 green chips diagonally, how can we place the rest of the 3 chips, 2 reds and 1 blue? Since we only have 3 squares, we have to use the only blue chip to separate the 2 red chips. Therefore, the only blue chip has to be in the corner square, and the 2 red chips are in the rest of the 2 squares. And this certainly satisfies our condition. So we only have one way to place all the chips in this subcase. Then let's consider the next subcase. The third color of the chips, which is green in our scenario, are not placed all in the diagonal squares. So let's draw a new grid of squares. So we'll have a cleaner view. Good. So we start with this red and the 2 blues here. So now the question is, we don't want all the 3 greens in the 3 diagonal squares. Then what should we do next? We only have 3 squares left. This, and this, right? And the question is, can we place a green in one of these 2 squares? The answer is no. If you do that, then you virtually eliminate all these 3 squares for the green chips, right? Otherwise, one of that green will be adjacent to this given green, which means that the rest of the 2 greens has to be in these 2 squares, which is obviously impossible. They will be adjacent to each other. Therefore, these 2 squares are out of the question for our green chips. Then let's remove them. Now our only choice is the corner square. We can only put a green chip in the corner square. So this is a green. How do we place the other 2 green chips? Then we have 3 choices here. I'll use different colors. One choice is these 2 squares. And the second choice is these 2 squares for the remaining 2 green chips. And the third choice is these two squares. Now let's consider them one by one. We'll use the yellow color for the first possible case. So let's start with a new grid of squares again. In this case, we know that this corner square is a green, and here is a red, here is a blue, here is a blue. And we want to place the two greens here, right? And we still have two reds and one blue. In order to separate the two reds, so one of it has to be in here. And as for these two squares, we can only place a red here and a blue here, not vice versa. Otherwise, these two will be adjacent, right? Therefore, we know that this is good. And for the second scenario, let's say we have a new grid of squares. And we want to place our green chips here, here, and here. And we start with a red in the corner and two blues here. And this scenario is actually symmetric to the first case, right? We have two reds and one blue to place in these remaining three squares. And therefore, one red has to be here. And the next red has to be in here. And the blue goes to this square. This is the only way we place all the chips. So this is also good. And now we will see that the third scenario is virtually impossible. Because if we put a green here, and a green here, and a green in this corner as well, we have a red, a blue, and a blue. Now how do we place the two reds and one blue? Since we have blues here and the blues here, so the center square has to be a red, right? And then how do we place the last red? That has to be adjacent to this center red. Therefore, we know that this scenario is impossible. So for the second subcase, we only have two possible ways to place all of the rest chips. So now let's come to the second case. Different colors for these two squares. And I'll draw a new grid of squares. So this is our new grid of squares. Since we have a red here and two different colors for these two squares, therefore we only have two choices. It will either be blue-green and green-blue, right? We only have two choices. And by symmetry, let's say we have blue and green. And then what's next? Should we consider the red chips? The answer is no, because this red chip is isolated in the corner and separated from the rest of the picture by these blue and green. And then the other two reds will be like a free variable. They can be placed in anywhere, and that'll make things more complicated. Therefore, we shall only consider the two greens or the two blues. So let's consider the two greens, right? Since we have a green here, these two cells can't be green. Therefore, the remaining two greens has to be placed either in this square, this corner square, or this square. We have four possible squares to place the rest of the two green chips. And let's consider all the possibilities. So the first possible case is the two greens in here. Let's label the squares with a number. So the two green chips can be in the two squares with a label 1. That's one possible case. Or the two green chips can be in these two squares, which are labeled as number 2. And we have a third possibility, which is in these two squares, labeled with number 3. And you'll see that only these three possibilities are possible. And let's analyze that one by one. We'll browse down a little bit. Good. So we'll start with a new grid of squares. So let's say this is our grid. And this is R, this is B and G. These are our starting squares, right? So we keep them the same. Now let's look at the first case, number 1. The 2 greens are in these 2 squares. So here is green and here is green. And now we want to consider the 2 red chips and the 2 blue chips. Since these 2 squares are adjacent, the center square must be a red, right? And we have one more red, which has to go to this square. Then the 2 blues will be here and here. Therefore, we have a unique way to place all the other chips. So this is good, but we only have one way here. And now let's consider the second scenario. The 2 greens are in these 2 squares, labeled with number 2. So let's look at this grid of squares. So we have to make many copies of this grid of squares. And we need to copy these 3 starting squares to these grids. So that will be B, R, and G. And then for these number 2 squares, we have green. So this is green, this is green. And again, let's consider the center square. Since it's adjacent to this blue, so it has to be red. And for the third red, it can either go to this place or go to this place. And we know that this is certainly wrong, because if the last red go to here, then the 2 blues will be in these 2 squares. Then they will be adjacent. So that is bad. We need to put a red in here, and then blue here and the blue here. Therefore, we know that this layout also satisfies our condition, and we only have one way to place the rest of the chips. So we only have one way, and that is good. In the end, let's consider this case. If we put the remaining 2 greens into these squares labeled as number 3. So let's come with a new grid of squares. And the number 3 are these 2, green and the green. And again, we copy these 3 starting squares to this scenario. So that will be R, B, and G. And in this scenario, we want to consider the rest of the 2 blue chips. Since we have a B in here, then these 2 neighboring cells has to be red. And then the last 2 blue chips has to go here. So this is a very easy scenario, right? So this is good. It satisfies our condition, but it only has one way to place all of the chips. Therefore, we know that the placement of these 3 green chips uniquely determine how the other chips are placed in this grid of squares. Therefore, we have 3 possibilities. 1, 2, 3. So we need to multiply a 3 in here. Up to now, we've listed all possible ways to place the 9 chips in this grid of squares. And then we need to do a sum up. So let's do a sum up. So we have 3 times 2 times, that's here, 1 plus 2, 1 plus 2. That's for the first case. And then plus the number of ways in the second case, which is 2 times 3. And now let's do the calculation. It's 3 times 2 times 1 plus 2. That will be 2 times 3, plus another 2 times 3. Therefore, we have 3 times 6 plus 6. That will be 3 times 12. So the final answer is 36. This is our solution. And now let's check the 5 choices. E is our choice. So this is method 1. Now let's look at the second method. As we said, in the second method, we'll still consider an extreme case to start with. So in the second method, let's draw this grid. And in this time, we don't want to look at the corner squares again, because they are of the same property, right? And that they have the fewest number of neighbors. In this method, we want to consider the contrary extreme case, and that will be a square with the most number of neighbors. Then which cell in these 9 squares satisfy our condition? It's certainly the center square, right? Only that one has the most number of neighbors. It has 4 neighbors. Here, 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 and here. Alright, so we'll place a chip in this square. Then how many ways can we place a chip in it? That will certainly be 3. We have 3 colors, red, blue, or green, to place in this square. So that will be 3 times. And by symmetry, we can choose any of the 3 colors in it, right? So let's say it's a red. Then in next step, we want to consider the other 2 red chips. Since this square has a lot of neighbors, none of these neighbors can be a red. Then we know that the other 2 reds has to be in the corner squares. But still, there are different ways to consider these 4 corner squares. And this is the right place that we do the casework. And how do we do it? One natural way to consider it is we choose 2 squares that are in the same line, either vertically or horizontally. So let's describe that as 2 corners in a line, either vertically or horizontally, right? And the second case will of course be otherwise, but actually we can describe it in a better way. If we place the 2 red chips otherwise, that means the 2 red chips either in these 2 cells or in these 2 cells diagonally. So let's denote that as diagonally. Good. Then let's start with case 1. We want to choose 2 corners in a line vertically or horizontally. Since this square has 4 sides, we can choose 2 corners on the top, or 2 corners on the right, or 2 corners on the bottom, or on the left. Therefore, we have 4 ways to choose 2 corners satisfying the condition. And by symmetry again, we can choose any of the 4 pairs of corners, right? So let's say we choose the top 2 corners. Then that will be red chip in here and the red chip in here. Then what's the next step? Which of the rest of the squares are the most special? It's certainly this square, right? This square is surrounded by 3 reds, and it's isolated. Therefore, we can choose any of the remaining 2 colors for this square. Then we have 2 choices, right? It either can be a blue or a green chip. And by symmetry, let's say we placed a blue chip in this square. And then for the rest of the 5 squares, we need to place 3 green chips. And that is very obvious. We only have 1 way to place these green chips. There are too many of them. We have to separate it from end to end. So that means a green chip in here, a green chip in here, and a green in here. Then the 2 blues got to be in this corner and this corner. Therefore, once after we determined this chip, then the layout of the rest of the squares is uniquely determined. Therefore, we only have 1 way to place all other chips. Then this is case 1. Now let's look at case 2. For case 2, we want to place the 3 red chips diagonally. And as we said, we have 2 ways to place them diagonally. The center got to be a red. Then the two ways got to be this way or this way, right? We have two ways to place the rest of the two red chips. By symmetry, let's say we place the two reds here and here. And then we realize that these three red chips virtually cut this grid of squares into two parts, the upper corner and the lower corner. So we have three squares in the upper corner and the three squares in the lower corner, right? And then let's start from the upper corner. We want to consider in this particular corner square, what kind of chip can we place in here? And we have two choices. It can be either a blue or a green chip. So we have two choices. And without loss of generosity, let's say we put a blue chip in it. If this is a blue, and immediately we know that these two neighboring squares has to be of different color, then they have to be green. Green here and green here. Now let's look at the lower corner. And we still have two blues and one green to place in these three squares. And we have to separate the two blue squares. Therefore, there is only one unique way to place these two blues separated by this green chip. The choice of this square uniquely determined the layout of the rest of the picture. Then we know that we only have one way to place all other chips. Then up to now, we've got all possibilities to place the 9 chips in this grid of squares. These are all the possible ways. Let's do a sum up. So we have 3 times, here case 1 is 4 times 2 plus case 2, that's 2 times 2. Alright, then we have 3 times the first 4 times 2, that's 8, plus 4. And that equals 3 times 12, which is 36. This is our final answer. And now let's look at the choices. So again, we have the choice E as our final answer. And before we end this video, let's do a quick sum up. We introduced the 2 methods to solve the problem by choosing the starting square differently, but all by extreme scenarios. In the first method, we select a square with the least number of neighbors. And in method 2, we select a square with the most number of neighbors. And by comparing the process of analysis, you probably notice that maybe the second approach is better, and I do agree with that. However, in the actual exam, you never know which idea comes to your mind first. And even if for this slightly complicated approach, method 1, you should still be able to finish all the analysis in about 6 to 8 minutes. And still, that's a very reasonable amount of time. Remember, this is the last question in this AMC10 test. Therefore, you should have saved sufficient time from earlier, easier problems. Therefore, I'd say that method 1 is still a viable approach. Alright, that's so much for this problem. If you like this video, please give it a like and subscribe the channel. If you have questions, please leave a comment.